So as we have discussed, rank of a matrix is number of dimensions in the output space of the corresponding linear transformation. So linear transformations we have already discussed. For example, we are talking about a matrix A. So if we apply this matrix A on a vector, let's say u, and we get another vector v. We have discussed in the previous vector that this vector and this vector can be of different dimension. Means it is quite possible that we apply a matrix on this vector and we get a three-dimensional vector here, or we get a 10-dimensional vector. And it is quite possible that we apply a matrix on 3-dimensional, we get 2, 3, 4 or any dimension vector. It is possible, right? So we have seen that when we were using these notation Rm to Rn, this is the how we represent a transformation which is used by a matrix of dimension n cross m. This kind of thing we have seen in the previous tutorial, right? So the dimension of the output space is known as rank of the matrix. It is not the thing that it will always be n. It can be at max m or n, whichever is lesser. So it can be, if you are using a 2 by 3 matrix like this, then maximum rank can be 2, as we have seen in the animation, right? If you are using a 4 by 3 matrix, then maximum rank can be 3, so like that. So there are few other ways to understand the rank. Ranks are basically the number of unique, or I can say linearly independent rows of a matrix. When we write any matrix, it is unique rows. For example, if I just write this matrix 1, 2, 3, and here I just write 4, 8, 12. Now because I have written a matrix like this, you can say that this is a 2 by 3 matrix. But actually if you look at this matrix carefully, second row is nothing but the first row multiplied by 4. Is just the linear combination of the first row, right? So there is no point of giving this information again. This information is redundant. I will talk about this in context of applications when you apply machine learning models, data science models, or when you store data. What does it mean when I say the row or column is redundant or linearly dependent? We will talk about that. But here this information is not adding anything. So in this case, rank of this matrix is just 1, right? And similar thing we can check for the columns. So if we look at the columns, number of unique columns or linearly independent columns would be rank of the matrix. And surprisingly, whatever way you compute for a bigger matrix, suppose you have 10 by 8 matrix, if you look at rows or if you look at columns, these two will give you the same answer. Rank of a matrix is always unique, whatever way you calculate it. Now, we have already discussed rank cannot be larger than smallest dimension of the matrix. So if it is a 2 by 3 matrix, maximum rank can be 2. So this we have already discussed. Now, non-zero determinant indicates that it is a full rank matrix. Full rank matrix means if you are making a transformation of vector u and u is m dimensional vector, so your resultant vector v is also m dimensional. There is no loss of dimension when you are doing this transformation using AU equal to V, right? Then we say that this matrix is a full rank matrix. And how to check if the matrix is full rank matrix? There are various ways. As we have discussed, you can check the linearly dependent, independent rows, but the easiest ways to ascertain that it is a full rank matrix is you check the determinant of the matrix. If you are not sure what is a determinant, we will cover that in a separate video, the geometrical meaning. There is just a formula to complete determinant of a matrix, and if the determinant is not 0, then you can say that it is a full rank matrix. So determinant of this matrix would be AD minus BC. This is just a formula for a 2 by 2 matrix. We can see formula for other matrix also. So you get an idea that it is a full rank matrix if the determinant is not 0. Now, you might be wondering why we are putting that much emphasis on rank of a matrix. Is that a useful thing to understand? Yes, it is useful, because I hope you all will agree with me that solving system of linear equation have applications in many areas and many applied domains, right? And to solve system of equations, you need to have solid foundations of matrices, right? So we will discuss later on how we can solve system of linear equations using matrices, and we will not do that much math here, but I will just give you some intuitions and idea. And there you see that there are three possibilities, that for a system of linear equation you have unique solution, or you have no solution, or you have infinite many solution. So if you want to see whether a particular system of equation has unique, no or infinite many solution, it is helpful there to have an understanding about the linear transformation or rank. If it is a full rank matrix, or if it is non-zero determinant matrix, it means you will have a unique solution for that system of equation. We will discuss these things when we will talk about solution of a system of linear equations. One more thing I would like to tell you is column space of a matrix. If these things you find very abstract and you want to leave the discussion as of now, you can leave it, but I would say these things are all very related, just different names to understand the similar concept. So the column space of a matrix is the set of all possible outputs of the linear transformation. Suppose A is the matrix corresponding to the linear transformation, then what does this represent is, suppose A is this matrix A, B, C and D. I am just taking an example of a 2 by 2 matrix associated with the linear transformation. In this matrix, these columns represent where the basis vector lands. If you remember from the previous tutorials, earlier we have discussed that the basis vectors, suppose we are taking the standard basis vectors 1, 0 and 0, 1. So these are the basis vectors in the original space, and after applying a particular linear transformation where these basis vector lands, so where I hat lands and where j hat lands, the coordinate of those points, if we write these as columns of the matrix and we apply this matrix on a vector u, it is equivalent of the same linear transformation, and we can write it as matrix vector multiplication. So these things we have discussed in our previous tutorial. If you are not sure what are these things, please go and watch those videos. So we are talking about column space of a matrix. So column space, why the name is column space? It means it represents all possible linear combinations of these columns. So basically, what are all possible outputs of the particular linear transformation? All possible linear combinations of these two columns, or we can say the span of the columns of the associated matrix. Means after applying the transformation, what all outputs are possible. So this is one definition of column space of a matrix. And we can also say that rank of a matrix is the number of dimensions in the column space. If you are not sure how, you might want to revisit the definition of rank of a matrix. The number of dimensions in column space. Suppose A is the original matrix associated with some linear transformation, and we denote column space of the matrix by CA. So number of dimensions in CA, what is that? Number of dimensions in CA, it is equal to number of vectors in the basis of CA. And the number of vectors in the basis of CA is equal to number of linearly independent columns in the matrix A, and which is known as rank of the matrix, as we have just defined. So basically these are one or two different ways of defining the same column space of a matrix. If you are finding these things messy, I would suggest you that you need to revisit the definitions of each and every terminology: rank, column space, dimensions, basis, linear independence and everything what we have discussed in the previous tutorial. Stay tuned. Thank you for watching.